Okay, good morning. First of all, my apologies for the mistake yesterday, and so thank you for pointing that out. And so you should have another copy of yesterday's handout, so destroy the one you got yesterday and use the new one. And the material on the website is hopefully we'll have better luck today. Right, so where are we? Okay, so this is today weather chart, midnight tonight. And what we see, this is a really typical autumnal pattern. There's a low pressure out in the Atlantic, and here's some fronts. Now, one would naively perhaps think that, oh right, we've got a big low pressure out here, here's a load of fronts, they're going to come charging across us and we're going to have a wet week. But the weather doesn't always play out as simply as we think. Actually, what's going to happen to this thing is going to track northwards. And often they do. The most common, the main storm track in the Atlantic is in this region here. And we're at the southern edge of the storm track. So you can see, if we look at what actually the forecast models think is going to happen, so this is the Met Office forecast model. The front, when it comes over, will be very weak, and actually by, so this is midday tomorrow, it's kind of weak, occluded front. I'm saying it's weak because there isn't very much change in the isobars, and the pressure is quite high. And as you can see, high pressure is coming in from the south. We have this other large low here. Another feature then, this we'll see in a minute, but this is a region where low pressure systems are generated in the western part of the Atlantic. So this, generally speaking, the sort of birthplace of depressions is around here, around Newfoundland, and they basically track across the Atlantic. Sometimes they spawn secondary depressions around us, but that's where the big ones start. Well, we'll have a look at that in a bit more detail in a minute. Okay, so just to pick up on a feature from yesterday. So this is now looking at the upper air chart, and as before, colours are average temperature in the low part of the troposphere, and the black is denotes the flow of the jet stream. So we've got a jet stream that is flowing over the top of this high. Remember, there was a high pressure to the southwest and high pressure to the east. Nothing much has changed. This jet stream continues to flow in that direction. The split is a little bit less obvious, but there's a bit of a split around this cutoff flow here. That doesn't look a particularly malevolent feature. I don't know if you saw any of the news reports last night. They have had extraordinary flooding in southwest France from this feature here. So these somewhat boring looking features actually can end up, and as you can see from this chart, it's an upper level feature. There's no real surface feature there at all. The white lines don't show very much at all. What you get in this case is a lot of deep convection, and if I can show that by picking up the satellite image, whoops, possibly better if I do that, and the convection has moved away into this region here, but yesterday it was over here, and they had a lot of people lost their lives, I think. So again, you can see this throughout this period of the lectures, we've seen these large thunderstorms in this region in the Mediterranean. Okay, so yesterday I was talking about convergence and divergence. Now this plot here shows it's just the wind speed at 300 millibars. So that's what the colours are. So the colours denote wind speed, and these are in knots. So divide by 2 to give you meters a second. And then this jumble of colours, of lines, these white lines denote the patterns of divergence. Okay, so it's really hard to see. But what I was pointing out yesterday was at the entrance to the jet, there's a little plus there and a minus there. So that's the dipole pattern that you get at the entrance of a jet stream. Convergence here, divergence here. And then at the exit of the jet stream, which is here, we've got the opposite. There's divergence on north of the jet and convergence south of the jet. So again, that's consistent with the kind of thing that we were looking at yesterday. What is perhaps more striking when you look at these patterns, though, is that in this region here, all the values, they tend to be positive values. Then here, there are dotted lines, so they tend to be negative values. That's not really consistent with this idea of the convergence and divergence being confined to the jet exit and entrance. So we're going to be picking up that theme in the lecture and showing why that is. Because in fact, you look horrified. Yes. Any questions on that? That's actually quite a hard picture to visualize. Hopefully you'll understand better when I go through the lecture. Also, the other thing that we looked at was just the variation of winds with height. So yesterday I showed a cross-section of a front. It's not as easy for me to do today because the front is weakened quite a bit. But if you look across the front, basically you see these temperature, the temperature changes. Obviously a front is a region of temperature gradient, and the front tilts with height. So we've got this idea that the frontal surface tilts like this. And typical tilt for a cold front is around 1 in 100. So 10 kilometers, 1,000 kilometers. So it's actually they are quite shallow things, fronts, but obviously on this scale they look fairly local. But the obvious thing that is also associated with fronts, so this is a diagram, and this is taken from Manunicast, which is the model that we run here. It gives me some graphics that I can't get from GFS. And this is a picture from around, well, it's a forecast for now, basically. And it's showing 7 o'clock, actually, Tuesday the 16th, the 13-hour forecast. This is at 700 hectopascals, and the colour scale is meters per second. Okay, so it's a slightly different colour scale. And what you can basically see is these are the strongest winds. And if I compare that then with the same thing at 300 millibars, it's pretty obvious that you've got this increase of wind with height. The scale is now the same on these two graphs. So the same colours. So this. All I want you to get from this is the qualitative picture that the wind speed is increasing with height. But the nature of the pattern is very similar. And you've still got this is the jet stream, and beneath it you've still got strong winds, but the winds increase with height. So we've got the same kind of feature then. So this is again associated with a front. So we've got a temperature gradient across the front, and we have an increase in wind with height in the region of the front. So we're going to be looking at that. So I'm going to be looking at two things today, which is divergence and convergence patterns associated with these Rossby wave type, these undulations in the jet stream, as we shall show. These undulations also cause convergence and divergence, and I'll be looking at why the wind changes with height. Yeah? So that's what I'm going to try and do today. Any questions? Right, good, okay. So let's crack on then and see how we get on with this. Okay. So this is just a recap of what I did yesterday. Because in pressure coordinates, the three-dimensional divergence, 0. The horizontal convergence and divergence is what we're interested in. And this is coupled to vertical velocity, and in fact, determine patterns of vertical velocity. So, although it's always a bit dangerous to talk about which is the chicken and which is the egg, in this case, it tends to be these patterns of convergence and divergence which force the vertical velocity on this scale. Now, in turn, these convergence and divergence are mainly a property of the ageostrophic wind. So first order, the divergence of the geostrophic wind is 0. It's not absolutely true, it's just, it's a lot smaller. It's sufficiently smaller that most of the convergence and divergence comes from this ageostrophic component, which is in itself, of course, much smaller than the geostrophic. but nonetheless, it flips to the other way when you look at the divergence of the flow. In turn, the ageostrophic wind is proportional to acceleration, and we saw this typical pattern that I was referring to just now. The jet stream sets up convergence and divergence at the entrance and exit, because at the entrance and exit of a jet stream is where we have acceleration, the flow speeds up and slows down. Yeah. Okay, but acceleration, this continues to be the case, but acceleration isn't just about speeding up and slowing down. Velocity is a vector, and acceleration can mean changing direction as well. So now I'm going to look at the effect of changing direction on the flow. Okay, so that's what this plot is supposed to be. So let's consider circular flow around a low pressure center. So this is, the low pressure is in the middle of all of this, and here we have circular flow going around the low pressure. So U is the horizontal wind, and it's basically going around in a circle. Okay, that's fine. In that case then, since the wind goes round in a circle, without knowing any atmospheric dynamics at all, you know that there must be a net centripetal force, U squared over R. That's just the normal centripetal force. If it doesn't, you know, that's true in all cases of something going round in a circle. The actual force is, of course, pressure gradient force, which points inwards towards the low pressure, Coriolis, which in this case points outwards at that point P. And effectively, there must be an imbalance between these two. This one must be stronger than that one in order to allow the wind to blow round in a circle. And we express that by looking at the momentum equation. So this says that the acceleration is the resultant of the pressure gradient and the Coriolis force. Okay, well what we can do here is to express this U squared over R. What we've got is a fortunate situation here where everything is actually collinear. Although this is a vector equation, you can see that it's going to collapse to a scalar equation pretty soon, because they're all in the same, along the same line, and therefore you don't need vectors really. Well, to get there, we can note that we can express this direction. Now, this is obviously K cross U gives you an inward unit vector. An inward vector. K cross U, U over R, K cross U then expresses the vector form of this. So this is the scalar speed, and that's the vector wind. So we put that in the equation up here. U over R, K cross U, that's just the resultant, and we've got these two terms here. And so we can take this one over to there, we put a K cross U twice in this equation, we take that over there, we get U over R plus F, and then multiplying throughout by K again, in the usual way, if you multiply, K rotates something by 90 degrees, so if you apply K cross again, you get, it just goes backwards, and so that changes the sign here, K cross grad phi, so U over R plus F times the vector U is K cross grad phi, but we know, because by definition that's F times the geostrophic wind. So we have U over R plus F, U equals F UG, and that expresses this balance of forces, imbalance of forces, which allows the parcel to go round in a circle. Yeah, so any questions on that? Okay, unfortunately this thing has a name, this equation. It's called the gradient wind equation. I have no idea why. It's a completely silly name for flow around in a circle, right? But that's the name that it's given to it. Gradient wind equation. I don't know why, who came up with this name. Here's the bit of the last slide. Like I pointed out on the diagram, those two, the wind and the geostrophic wind, they must be collinear. Well, it has to be in this equation if that times u is that time. The scalar times one is a scalar times the other. Then they must be collinear. Direction must be the same. And so we have a scalar equation. So this is a scalar equation here. All of these terms, all of these u's now are just the speed, okay? So whereas with a vector you can have a negative wind, in a scalar equation you can't have negative wind because it doesn't make any sense. Okay, so that's the so-called gradient wind equation. If you look at the handout that I gave for today's lecture and turn it round, you will see that there is an example sheet there. And there are a number of examples there where you basically find the gradient wind. You solve this equation. To solve the equation, you have to use the usual quadratic formula. Okay, it's the minus b plus or minus the square root of and so on. Yeah? So you just have to basically plow through using that equation, using that formula. Sometimes people say, surely it can't be that difficult, but obviously it is. When you solve the quadratic, you end up with two solutions. Yeah? Quadratic equation has two solutions, and you have to use your skill and judgment to work out which is the right solution. Yeah. Okay. So you ought to try doing the problems on the sheet. I mean, the key things are that obviously the wind can't be negative, so once one of your solutions is negative, you can throw it out straight away, because wind speed cannot be negative. But the other is, if the wind, you know that if you're dealing with a low pressure system, if you simply examine this equation, what does it mean? Well, clearly these two terms, if R and F are positive, then in order for those to balance UG, then U must be less than UG. It's just arithmetically predetermined in that situation. For positive R, U is less than UG, and wind around a low is slower than geostrophic. It doesn't mean to say it's absolutely slow, because the strongest winds that we get are around low pressure systems. That sounds a bit odd. This is just saying it's slower than it would be if it were geostrophic. Okay. Now, of course, why am I saying for positive radius of curvature? How can you have a negative radius of curvature? I'm about to show you. Okay? So, mathematical trick coming up. This was flow around a low pressure center. What happens if we go around a high pressure center? Well, obviously the flow goes the other way. So it's going this way. And the centripetal force has to be the same. Centripetal acceleration has to point in towards, in this case, a high. Only this time the pressure gradient force points outwards and the Coriolis force points inwards. And it's the Coriolis force that must be dominating in this case, rather than the pressure gradient force. So, rather inconveniently, because of the way the vectors work, this time round, the centripetal acceleration is minus u over r, k cross u. Okay? The centripetal acceleration is in the same direction, but u isn't, it's pointing the other way. So not surprisingly, an inconvenient looking minus pops up in our equation. It's done like that. Oh, so here we are, here's the equivalent. So unfortunately it looks as though we have to have one equation for flow around a low, and another equation for flow around a high. Nah, don't want that. How do we get out of this? Well, we let the radius be negative. Hey ho, we've solved the problem. So, if we define R, in this case, for the wind going around in this direction, this is in the northern hemisphere, so clockwise in the northern hemisphere would be negative R. So we attach a meaning to something that is geometrically, there's no meaning to a negative radius. So, but it suits us as a mathematical convention to define R to be negative. And if we do that, we end up with the same equation as before, which is good, because we only want one equation. What we can see here, because in this case, r is negative in this equation, so now this term, this quadratic term in the equation, takes away from this fu. And so u must be larger than ug in order to balance the equation. Winds around a high, the wind around a high, is faster than geostrophic. So again, somewhat takes a little bit of digesting. Winds around high pressure are generally very light. But yes, they may be light, but they're faster than they would be if you just use the geostrophic wind to flowing around high pressure. Large high pressures tend to have big values of r, and so this term can be quite small. If u is small and r is very large, then obviously this term tends to be quite small. So in practice, around a high pressure, the flow can be very close to geostrophic, but that's just because of the way those terms play out. Yeah, so now we've seen that we've got differences from geostrophic. So what does that mean? It means ageostrophic, right? So something that's different to geostrophic is ageostrophic. When we looked at acceleration along the flow, we saw that the ageostrophic wind was perpendicular to the flow. Here, when we're talking about directional changes, we see that the ageostrophic wind is basically along the flow. It's a scalar equation. And so the ageostrophic wind in this case is positive and along the flow. In other words, it makes the flow faster, and for a low it makes it slower. Okay, so faster around a high, slower around a low. Okay, now then, let's come back to the jet stream. Gradient winds are all very well, but actually what we want to get at is convergence and divergence. Let's go that way. So here's a trough ridge pattern in the jet stream. These are the sorts of things that we've been seeing on the charts throughout this course. The ridge is a region where the flow is turning clockwise, and the radius is negative in this region here. So the flow is faster than geostrophic, and so the UA, the ageostrophic wind, is positive in that region. And similarly for the trough, the ageostrophic wind is negative. In other words, it slows the flow down. Okay, so what? What next? Well, let's draw that. Okay, so what we've got here, here's our ageostrophic wind this way, and here's our ageostrophic wind this way. And in this straight part of the flow in between, there's no curvature, and so in the absence of changes in the speed, then the UA is 0 here. So you've basically got a geostrophic wind in this part of the flow, and again in this part of the flow, and ageostrophic wind where the thing is curved. But you can see what's happening. You've got these arrows. So these arrows are pointing towards each other, basically. You have a region here along this branch, northwesterly branch of the Rossby wave, where you've got convergence, where the ageostrophic winds are converging, and the other way for the divergence on the other side. And so, if we draw this and just put those arrows in, so we have a region here of convergence, there's like C, which denotes convergence, and a region here of divergence. So, not only can we force convergence and divergence with changes at the jet entrance and the jet exit, but we also have the same thing around forced by these changes in direction. And that's what we saw when I pointed out earlier, when I was pointing out these dipoles at the jet exit and the jet entrance, that actually there seemed to be mostly convergence in this branch of the flow and mostly divergence in this branch of the flow. So you saw that on that somewhat confusing plot earlier on. Remember that downward and upward motion are related to what happens to the weather at the surface. In this region of the atmosphere, you would tend to promote anticyclonic growth certainly anticyclonic behavior at the surface. So in this region of the atmosphere, you would tend to get what? Well, suppression of convection. In other words, there tends to be downward motion there, and so suppression of convection, you would tend to get possibly clear skies even. Certainly in the free troposphere, boundary layer sometimes has a life of its own. Obviously things like proximity to warm ocean and bringing cold air over warm ocean, that can give you boundary layer cloud, but it's not necessarily going to give you anything deeper. Here is where you see, well, you can see convection, obviously, deep convection, or in fact growth of cyclones. So in fact, when we look at where cyclones grow, they tend to grow in this region of the pattern. I'm going to show you that in a minute, but let's see. Yeah, so I showed you these. I don't think I really need to dwell on that one. These are the things I showed last time. So convergence, divergence. This is just to link the top and bottom of the atmosphere, and just to show that the highs and lows are linked to those patterns aloft, and that's those slides I showed last time. What I'm going to just do here is to flip back to this one. Okay, so what I'm going to do is animate this. Okay, and I want you to keep your eye on this part of the plot. And what you see is the growth of these. This is a cyclone growing, and it's growing in this region downstream of the trough. So again here. So these troughs are coming out from the edge of the board, and you'll see as they come out of the edge of the board that the growth of low pressure systems is happening. It happens just to the on the cold side, because that's where the divergence is strongest. But this is, you can slow down a little bit now, but this is coming again. So this one here, again, it's on this western side of the trough, sorry, on the eastern side of the trough, on the downstream side of the trough, where you see these, again here, so another one here, again on the downstream side of the trough. So in this region, so it's starting off again. The same is true for this one that we're seeing around us today, only it's already formed. A little bit more difficult with the anticyclone, but we can see this anticyclone here is sort of downstream of the ridge in the upper levels. So there's this link. So when you're looking at where a cyclone is going to develop, you're always going to be looking in this kind of region here. It doesn't always happen. If you look in this particular region, it doesn't develop a cyclone at the surface. But certainly if we're looking out over this region where the sea surface temperatures help, so there we are, there's one of these cyclones blowing up in that region there. The reason that there's this sort of genesis region for cyclones off the coast of North America is twofold. First of all, we get a lot of these Rossby waves coming off the North American continent, and so priming the atmosphere with these divergence pattern. And secondly, you have a big gradient in sea surface temperature at the north edge of the Gulf Stream, and that gives you baroclinicity, as it's called, low-level temperature gradient, and this divergence aloft, and you get this growth in cyclones from, well, just the mechanism of cyclone growth. I'll say a little bit more about that next week. Okay, so that's the story about how convergence and divergence patterns. So you can see it's quite complicated in that you don't just have the speed of the jet stream, it's the way in which the jet stream changes direction, and all of this sets up these patterns of convergence and divergence. It's a bit difficult to see just from an animation like that, but that's if you want to do this, then it's a good idea to just sit down and just watch these for a little bit, and then your eye picks up fairly quickly what these patterns are up to. It's a lot easier to look at it on the screen than on there as well, because you can focus in a lot better. Okay, so there's convergence and divergence patterns. Now I want to just turn in and look at jet streams in a bit more detail. So jet streams, well, I've talked about jet streams, but why do we have jet streams? We know that jet streams and fronts occur together, horizontal temperature gradients, and now we're going to try and ask why. This is one of these geography book cartoons about the general circulation, so this is an entire hemisphere. Deep convection in the tropics driving the Hadley circulation, so we have this rising air in the intertropical convergence zone, poleward motion in the upper troposphere, and we form a thing called the subtropical jet stream at the edge of the Hadley cell, and then there's descending motion. This is where you have deserts around in the subtropics. And then we have north of that again, we have this region, this is the polar front, and this is the polar jet, and this is a sort of schematic of the front. So the polar jet and the front are closely linked together. There is a front associated with this one, but it's only in the upper troposphere. It doesn't reach the ground because it's a region of downward motion. Whereas in the polar jet, it's a region of upward motion. So what's going on? Well, okay then. Now I'm going to look at something a little bit different. I'm going to look at vertical wind shear. So by that I mean the gradient, the vertical gradient, I'm using pressure coordinates, so d by dp of the horizontal wind vector. Okay? So the rate of change of horizontal wind vector. This is the geostrophic wind. Now I'm going to confine myself to looking at the the shear of the geostrophic wind, because otherwise it gets very messy. Here's the geostrophic wind, 1 on Fk cross grad phi. So that's the standard formula. These are both vectors here. So it's K. We can express phi as G times the geopotential. So G over Fk cross grad Z. So Z is the geopotential height in this case. And so if you differentiate it, du by dp, these are both constants. Well, that's a constant. d by dp must commute with a gradient, horizontal gradient at constant pressure, right? So the whole thing, so it goes all the way through this equation, and you've got dz by dp. So it's the rate of change of z with p. And we know from, well, dp dz is pretty well known. This is the hydrostatic equation, minus rho g minus p, g over r times t. And so inside this bracket is dz by dp, which is 1 over this, minus rt over p times g. All of which, other than t, comes back out of this operator, because obviously this is an operator of constant pressure, and so p just comes straight out of it. And so there's a g on the bottom which cancels that one. The f is still there. The p, as I said, commutes because this is a constant pressure, and r is the one, again, a constant. So we've got immediately, with almost no effort, the vertical wind shear, the rate of change of gradient wind with pressure, is minus. So that tells us that it's going, minus, yes, K cross grad T. So this is the temperature at constant pressure. So when we think of the cross-section through a front, and we've got a gradient of temperature at constant pressure at all heights in the atmosphere, then that's going to result in a change in the wind with pressure. And this is the thing that where essentially the wind between 700 and 300 millibars increases in speed. Mathematically, it's good to put this p over here. So p times du dp becomes du g by d log p. That just makes the equation a little bit easier to write. Or because sometimes it's hard to get your brain around the fact that pressure increases downwards, we can go for this formulation, du g by dz, and so this is just multiplying this equation by the hydrostatic equation, dp dz, and so that gets rid of a lot of this stuff. Pg upon rt du dp, this is du dp again, so a lot of this lot cancels out, and you get ug by dz, g upon ft k cross grad t. This is called the thermal wind equation. It's a more sensible name than gradient wind because, yeah, well, it's got temperature in it, so T, that's good, thermal. What does the thermal wind equation do? Well, it basically relates the vertical gradient in the geostrophic wind to the horizontal gradient in temperature. This is a fundamental balance equation in the atmosphere. It's absolutely fundamental to the way that atmospheric models work, and it's fundamental to the ability of models to assimilate observation. Because if, for example, you know the temperature field, then you can derive the wind field. And how do you know the temperature field? You've got satellites up there. Satellites measure temperature globally. They measure profiles of temperature globally. From those, you can derive the geostrophic wind. Now, actually, that's not quite good enough, as we've shown. We need to know the departures from geostrophy, but nonetheless, that gives us a big help. This equation is valid, obviously, on the synoptic scale. When we come down to smaller scales, where the winds are often very different to geostrophic, then this equation doesn't apply, and that's one of the real problems with forecasting at the smaller scales, is that we don't have this kind of balance equation, and it's much more difficult to assimilate observations. So what does this do, this equation? Grad T points equatorwards in the troposphere. Obviously, it's warmer at the equator than the pole. So K cross grad T, so if you think about it, K is up, grad T is towards the equator. That tends to give you, that vector points towards the east. It doesn't matter which hemisphere you're in, because it works the same in both hemispheres, this one. So westerly winds increase with height in the troposphere, right? So the U by dz is positive, and that's why the winds away from the surface tend to be predominantly westerly. It's just because there's this large-scale equator to pole temperature gradient, and that basically means there's got to be a large-scale westerly wind component. It's a consequence, really, of the Coriolis force. The equator to pole temperature gradient is concentrated at fronts, giving a local maximum in the westerly wind near the tropopause. And that's what we call a jet stream. So we have this thing called a jet stream. Where's my picture? Here we are. So here's a region where we have this sharp change. I know it's drawn as a line here. You saw yesterday when we looked at the cross-section that it's actually quite distributed. But you can see this very characteristic pattern where the front is sloping. If this was a cold front, for example, the actual thing at the surface would be at the leading edge of the temperature gradient associated with it. And then you've got this sort of bullseye here above the front, which is the jet stream. So the front slopes down underneath the jet stream. In fact, at the surface, the front can be the other side of the jet stream. We also see this change in the tropopause as you go across the jet stream. So there's a big change from a high tropopause on the equatorward side to a low tropopause on the polar side. That could be as much as 4 kilometers or possibly even more in the middle of winter. Tropopause here, around 17 kilometers in the tropics, around 10 kilometers at the poles, and sometimes in these regions around the jet stream it can be even lower. So that's jet streams. So what I'm going to do now is just to do a little example of some of the calculations, the sort of things that you would do on the example sheet. Like I said, if you don't do the examples, you'll struggle if you try going into the exam. So it's important that you do these examples, and they're not assessed. You'll get marks for them, but if you go into the exam not having done them, you will not do well. You will struggle. Evidently, if they're not assessed, you can come and ask me about them if you can't do them. So here's an example of the sort of thing the sort of ideas that underlie that example sheet. So this is from a particular day. It's in July 2006, and here's our 300 and 700 millibar charts for this case. And as we saw, the winds, the lines I mentioned, there's more lines on here, closer together. So the wind speed increases with height. And so at 300 millibars, we see this southwesterly jet stream over the UK, about 100 knot winds, up to 60 meters a second wind in that over Ireland here. And then at 700 millibars, 3 kilometers altitude, we've got the same direction, but the wind speeds are a lot lower, about 20 meters a second. So we've got sort of 20 meters a second, 60 meters a second. Okay, so can we reconcile this? Is this consistent with the thermal wind equation? Okay, so let's look first of all at, this is at 300 millibars. Now, first thing I want to do is calculate the geostrophic wind. Okay, so I'm going to have a go at calculating the geostrophic wind. So what I've done is taken a bit of this line here, 111 kilometers is a degree of latitude, so I've taken this line here, which is I think 3 degrees of latitude, and I've just put it along there. So I know the length of that. That's that distance, well, it's 5.5 degrees of latitude, that line. So I've drawn a line between this contour and this contour, perpendicular to the flow across that jet stream. 952 decameters, 912 decameters. The difference between these is 40 decameters, 400 meters. Okay? So I've got a difference in height of 400 meters between here and here, height of this pressure surface. And so the difference in geopotential, G is 10, multiplied by 10, you get 4,000 meters squared per square second. So that's relatively simple to do. The difference, the distance again, you can just measure it off, and then I just drew it along here, and then that's, well, there's a scale on the map. I use a larger scale map, and so I was able to, well, that's 50 degrees here, that's 60 degrees there, and just a bit of work with a ruler tells you that that's 5.5 degrees latitude, which is 616 kilometers. Again, making use of the fact that on these charts, 1 degree is 111 kilometers. So this is how you go about constructing some of these things. How do you know what the distance is? Well, you just remember that little rule of thumb. So grad phi, which is basically the gradient of geopotential, is 4,000 divided by 616 kilometers. We've got to put it in meters, and so we get and that gives you 0.0065 meters per square second. The geostrophic wind is 1 over Fk cross grad phi. So obviously, the geostrophic wind is perpendicular, which is good because it does tend to be lying along the isobars. F is 1.2 times 10 to the minus 4 per second in this region here. And so if you divide it, you get 54 meters a second. And there's around, it's pretty consistent really with the measured winds. And knot is 0.514 meters per second. So that's not bad. It's a little bit low, but it's pretty, well, it's pretty surprisingly accurate, to be honest with you, given how crude that calculation is. And you do get, I mean, this isn't a special case that I chose because it gives good answer. It's the kind of thing you get. So that's pretty good. Anybody confused about this? Not sure what I've done there? I hope I've walked my way through this whole fairly slowly with you. Okay. Again, have a look at this example on the on the website. Again, we've done the same thing now at 700 millibars. I won't go through the whole calculation, but once again we have two. This is 316 and 300, so now we've got 160 meters of difference. That gives us a delta phi of 1600. Same kind of distance between the two, in fact, and so we get a speed of around 23 meters a second, which is 45 knots compared with 45 knots measured in that region. So surprisingly good again. So the geostrophic wind, because it's pretty straight flow there, is being represented quite well. What about the difference? What about the thermal wind? Well, this is a bit more tricky because obviously we need a temperature. Now it turns out that on these old-fashioned charts they actually plot the temperature. So this number here is 5 degrees. The station is Camborne at the tip of Cornwall. And I'm going to compare that to one of the, this is Valentia, the station that we've looked at in Ireland, that's -1. So there's 5 degrees here and 1 degree here, so roughly 6 degrees maybe. And then when we look at this one, -37 and -40, the difference in temperature is around 3 degrees. So now we're really pushing it a little bit and saying, well, the average is about 4.5 degrees of those. Okay, the difference, the distance between these two stations, it's 3.7 degrees latitude, 400 kilometers, and so we get a delta T of 1.13 times 10 to the 5 -5 Kelvin per meter. And then we go through and look at the difference in geostrophic wind. Well, obviously, this is using the pressure formulation because these are constant pressure charts, and so we have minus R on F, right T, so the difference in U, difference in log P, and we go through and calculate this using the various constants, and it gives us a number of 24 meters a second. The actual difference between the two winds was about 30 meters a second, so it's not as accurate as the previous calculation, but as you can see, trying to estimate temperature from numbers like this is pretty crude. So it is, certainly qualitatively, it's giving you a reasonably accurate depiction of this particular jet stream. Okay? The thing to note is obviously that there are details. I mean, taking a spot measurement of temperature is not a sensible thing to do, to be perfectly honest. I would be better off looking at some model data, but that's a nice example and it's quick to do. And you know, the intention isn't to show you anything more than the method that you apply in this case, rather than, you know, the actual result is irrelevant here. But if you need, some of those questions will require you to use this kind of methodology. So it's just to give you a reference point when you're doing the problems on the problem sheet. That's what that is all about. Any questions? Surface chart on that day does indeed show a front, so as you might expect, given that there was a jet stream there, from what we've learnt today, jet streams and fronts go together, so there you are. Doesn't matter what sort of front it is, temperature gradient and the front are together. So I'll stop there. If you've got some questions, issues, stunned silence. Okay, there you go then. Any questions, obviously, please drop me a line or come and see me after the lecture. Now, one of you's got that clicker thing. All yours.
All right. Is it good?
Who knows? Find out in January.
Good point.
Here we go. Right, there's a little plastic here.